So, welcome back to the course. So, in the today lecture we will go further and we will try to find out that how the self-adjoint operator are used to find out the green functions, and then we will go for the how the Sturm-Liouville problems can be solved and then their properties. So, this is the lecture 13. So, in the previous classes we have discussed that if my operator LU is equal to A naught is a function of x. So, this is A naught x, A1 x u dash plus A2 x u. So, this is my linear differential operator with some boundary condition Bu is equal to 0, then we know that its adjoint operator, the L star V, can be written as A naught x V double dash plus 2 times A naught dash minus A1 V dash plus A naught double dash minus A1 dash plus A2. So, that is my corresponding the adjoint operator. Now, what about if I want to find out that L star is equal to L? So, this is the definition of the self-adjoint operator. So, from here I can say that this is possible when my 2 A naught dash minus A1 should be equal to A1. So, from here I will get that 2 times A naught dash should be equal to 2 times A1. From here I can say that my A naught dash should be equal to A1. So, my in that case from the this also I can find that the A dash minus A1 dash plus A2 should be equal to A2, and from here I can say that my A naught double dash should be equal to A1 dash. This is again taking the derivative of this A naught dash. So, if from here I can say that the L star is equal to L if and only if my A naught dash is equal to A1. So, if this is true, then I can say that my corresponding differential operator is the self-adjoint operator. So, this is the self-adjoint operator. So, for example, I take the differential equation 1 minus x square u double dash minus 2x u dash plus some lambda plus 1 u equal to 0. So, this is the Legendre equation we know. So, this is Legendre's equation. So, in this case this is my A naught x, this is my A1. So, if you see that the A1 is equivalent to the derivative of this one. So, in this equation I can write as 1 minus x square u dash the whole dash plus lambda plus 1 u equal to 0. And now, from here now if I take the derivative of this, then I will apply the product rule. So, it will be 1 minus x square, then the derivative of u dash. So, this will be u double dash plus the derivative 1 minus x square. So, this will be minus 2x and then u dash, and then the remaining part lambda plus 1 u equal to 0. So, from here we can write down that this is same as this equation. So, in this case I can say that if I find out the corresponding the adjoint operator, then we will find out that. So, this is we can say that the self-adjoint operator. So, in this case we can check that if I find out the L star, then it will be same as the L. Now, for this one, now we will try to go further and then we apply another equation. So, that is called the Sturm-Liouville problem. So, the Sturm-Liouville problem is that the general form of Sturm-Liouville problem, so I short form this is SLP, is written as, is given as L of, so yx, I will write like this one. So, this will be ax y double dash plus bx y dash plus cx y is equal to minus lambda rx yx. So, with the corresponding boundary condition. So, boundary condition is a1 y at alpha plus a2 y dash alpha equal to 0 and b1 y at beta plus b2 y dash at beta equal to 0. So, this is the mixed boundary conditions for alpha and beta. So, this is my corresponding boundary condition. Now, if in this case my bx, that is the coefficient of y dash, is equal to a dash x, then this is called self-adjoint operator, self-adjoint equation. Then it is called the self-adjoint equation. Means in that case my L star will be equal to L and my boundary condition B star will be equal to B. Then I will say that is self-adjoint equation or the system. So, in this case the given Sturm-Liouville problem will reduce to, so I will call it now some Px y dash dash plus Qx y is equal to minus lambda Rx yx. Okay. So, in that case I will just replace this one. So, you can say that now my Px is Ax, P dash x is Bx, and then my Cx I just replaced by the Qx. So, now my equation will be this one, and you can see from here that this is a self-adjoint. So, this is on the form of self-adjoint form. So, from here now my SLP Px y dash dash plus Qx y is equal to minus lambda Rx yx with boundary condition. So, I am taking the boundary condition with the boundary condition that y alpha a1 plus a2 y dash alpha equal to 0. So, homogeneous boundary condition I am taking, then the b1 y at beta plus b2 y dash at beta equal to 0. So, you can say in this case the x belongs to alpha beta. So, this is the system of equation. I can just write it that this is my equation number 1 and this is the corresponding boundary condition. I can call it 1b. Now, I want to find out this equation, I want to solve this equation. So, if you from here if you see this, the equation number 1, y x equal to 0 is always a solution, because y is here, if I put equal to 0, this will be 0, derivative will be 0 and right hand side is also 0, then y x equal to always a solution of this equation, the Sturm-Liouville problem 1, and then so this solution is called the trivial solution. So, this is called the trivial solution. So, we always go for to finding out the non-trivial solution of this equation. Further, the Sturm-Liouville problem I can write as this one is equal to, so this one, this equation I can write as now L star, not L star, just L, I just write down L, then my y x is equal to minus lambda r x y x. So, the Sturm-Liouville problem can be written like this one, and now I am just assuming that the function r x is always positive. So, from here if you see, then I can write that this is, if you just remember the matrices, then we know that if I write matrix Ax, A is a square matrix of order n cross n, and then if I write Ax is equal to some lambda x, where x and this x is the vector, then from here I know that if my x is not equal to 0, then this lambda is called eigenvalue, and then x is called corresponding eigen vector. So, that we know. Now, this linear operator is also the analogous to the matrix in the matrix theory. So, from here I can say that for this value of lambda, I can write this equation as L of y x is equal to lambda times minus lambda times r x y x. So, this equation if you see, it can be written as the eigenvalue problem depending upon this r x. Now, the question is that what is this r x coming from? So, let us take one example. Suppose I have a differential equation y double dash plus x y dash plus 2y equal to 0. So, this type of equation suppose I have, then from here I just, because you know that this is not a adjoint self-adjoint type, because the derivative the coefficient of y dash is 1 and the coefficient of y dash is x. So, from here what I do is I can take the integrating factor as e x dx, where x is the coefficient of y dash. So, from here I can write down e x square by 2, and then I multiply this equation with that e raised to power x square minus by 2. So, it will becomes e x square by 2 y double dash plus x time e x square by 2 y dash plus 2 e x square by 2 y equal to 0. So, from here I can write this equation as e x square by 2 y dash equal to minus 2 e x square by 2 y. So, from here I can write like this. Now, if you take the derivative of this one, it will be the first function derivative of second, so y double dash plus then taking the derivative of this one. So, E x square by 2 itself, and then taking the derivative of x square by 2. So, that will be x, so y dash, and on the right hand side this one. So, if you see this one, so this equation become now of the type p x y dash is equal to minus 2 r x y x. So, in this case my r x is exponential function, and you know that the exponential functions are always positive. So, this r x is coming from there. Whenever we want to make that the given equation is able to convert to the self-adjoint form, then we will able to find the value of r x. Now, so there is a one observation. So, just write down. So, definition: a Sturm-Liouville problem SLP with boundary condition with given boundary condition is said to be regular if each of the following, so each of the following conditions hold. So, what is the condition? The first condition is that my function r x should be positive. So, in the previous case it was the exponential function, and if I solve this equation, so my p x, this one, for all x belongs to alpha beta. So, p x is the coefficient of, if you see this form, so it is the coefficient of p x y dash dash plus q x y is equal to minus lambda r x y x. So, this is the form we are taking. The second one is that p x p dash x q x and r x are continuous on the given interval alpha beta. So, these are the continuous functions, and the third one is that the alpha beta, if you take the interval, is finite. So, if you are able to satisfy all these three conditions, then my corresponding the Sturm-Liouville problem is called the regular problem. Now, so there is a one theorem we want to define for any regular Sturm-Liouville problem. First thing we want to define. So, because I told you that this is a similar type of the eigenvalue function, so this is called the Eigenvalue problem. So, all the eigenvalues are real. So, all the eigenvalues are real. It means from here I can say that lambda is real for all. Second one is that eigenfunctions, because in this case if you see, then this lambda is called the eigenvalues, and then corresponding the solution we are getting corresponding to this lambda. So, this Vx is called eigenfunction. So, the eigenfunctions belongs to different eigenvalues are orthogonal with respect to the function Rx. So, they are orthogonal basically. Then the third property is so with respect to Rx under the inner product. So, I am taking the now defining the inner product. So, inner product, suppose I have two functions y n x and y m x. So, these are the two function I am taking, or you can just take the simple any function. So, I have two function f x and g x. So, I am taking the inner product. So, I am defining the inner product in this case, taking the integration from alpha to beta. R x, the function we are taking, this is called the weight function here, and then f x, g x, d x. So, this is the inner product I am defining. So, next third one is for to each eigenvalue there corresponds one and only one eigenfunction. So, this is the third properties, and the fourth property is that there are a countable infinite number of eigenvalues, that is we call it lambda 0, lambda 1, lambda 2, lambda 3 with corresponding eigenfunctions. So, that we call it y0, y1, y2, y3 and so on. And also because just now we are telling that these the eigenvalues will be, all the eigenvalues will be real. So, then we can define the ordering, and then we can put that one that. So, we can put the ordering of the eigenvalues, and then we can define the ordering that lambda 0 is less than lambda 1, less than lambda 2, less than lambda 3 and so on. So, we can put them in the ordering. And the fifth one is that let I take any function f x be any continuously differentiable function on the interval alpha beta, then then this function f x can be written as a summation of a series with coefficient a n and then y n x, where y n x are the eigenfunctions corresponding to the eigenvalues, where the coefficient a n can be written as, so I am taking integration r x y n x f x dx divided by alpha beta r x y n x square dx. So, the coefficient I can find out like this one, and then its value will be a n. So, these are the 5 properties. So, just now I will try to prove few properties. So, I can say that the proof. So, property 1. So, property 1 is that now I know that my L star is equal to L is a self-adjoint operator. Because it is regular, and if the regularity is, then it is self-adjoint operator, and then I can say that in this case my Px y dash dash plus Qx y is equal to minus lambda Rx y. So, from here if I try to take the derivative, so this will be again this will be equal to Px y double dash plus P dash x y dash plus Qx y is equal to minus lambda Rx y. So, this one I can define, and from here I can say that this and this, the derivative of y dash is a derivative of the y double dash, the coefficient of y double dash. So, from here this is a self-adjoint operator. Now, so this is a self-adjoint operator. Now, if you remember that the same thing is going to happen when we take the analogous form in the matrix theory. So, in the matrix theory we know that my Ax is equal to lambda x, then I just define the inner product in that form. So, in that case I know that the x transpose Ax Ay is equal to, so this can be written as x Ay inner product. So, this inner product we have defined. Now, this becomes equal to y A transpose x, this form. So, from here I can write this as, because if I take the, so if I define this one, then x transpose Ay taking the transpose. So, this can be written as y transpose A transpose and x. So, from here I can define my y transpose A transpose and x. So, this one I can write as y A transpose and x. So, this one I can write out. And from here if I know that if A transpose equal to A, then I can write that the corresponding eigenvalue lambda is real. The same thing we are going to do here. So, in this case what is going to, so I know that my L star is equal to L. So, I am now defining my L u v. So, this is equal to u L v by the definition of the self-adjoint operator. Now, if you see L u v, so this one is a type of eigenvalues problem. So, I can define from L u, I can define the lambda of u v, and this can be written as lambda I can take common, and then it is u v. Now, let us see what will happen if I define u and L v. So, in this case I can write this as u and L v is lambda v, because this is given to me. So, I will take the the conjugate of lambda and then uv. So, from here I can say that from this relation from here I can say that my L dash uv is equal to lambda uv. So, this is lambda bar. So, lambda bar is the conjugate of lambda, because we do not know, still we do not know what is the lambda, lambda is real or complex. So, I am applying just the properties of the green inner product. So, from here I can take lambda bar minus lambda and then the inner product uv equal to 0. And now I know that the inner product of uv is not equal to 0. So, from here I can say that the lambda bar minus lambda is equal to 0. So, from here I can say that the lambda bar is equal to lambda. So, that shows that lambda is a real number. So, from here I can say that lambda is a real number and lambda was the eigenvalue, corresponding eigenvalue. So, from here I am able to show that this is a real. Now, the second property is properties 2. I just want to define the proof of that one. Now, let I take two eigenvalues. So, lambda n and lambda m, and then the corresponding eigenfunction. So, eigenfunction I am taking yn and ym. So, this function I am taking. Now, I want to find what is L, y, n and ym. So, this one I want to find, because if you see that L star is equal to L and the corresponding B star is also B. So, this is self-adjoint system. So, in this case yn is also solution and ym is also solution of the equation. So, I can define the L yn ym. So, this one is inner product I want to define. So, this is minus lambda r x y n y m. So, this one is the inner product I am taking. From alpha to beta. So, minus lambda r x y n x y m x dx. Okay. So, this one I am just defining in this case. Now, what about yn L ym? So, again the same thing will happen. So, this will be equal to, so this I just call it n, it will be lambda ym alpha to beta r x dx. So, from here, and this is a self-adjoint, so both are same. So, from here I can write down. So, this and this both are same, because yn and ym both are the solutions of the L and L star, and they both are same. So, L star and is equal to L. So, these are the solution. So, from here I can write down. So, this becomes minus lambda n r x yn x ym x dx is equal to minus lambda m r x yn x ym x dx. So, basically this is the inner product we have defined. If you see that this is the inner product of yn and m, this is the inner product of y and m. So, from here I can write down just taking on the left hand side. So, it can be written as alpha beta Rx Ynx Ymx dx. So, this is we are defining and that is equal to 0. Now, I am taking ym is not equal to lambda m is not equal to lambda n. So, from here I, because these are the distinct, so from here I can define alpha beta Rx Ynx Ymx dx. So, this is equal to 0. So, from here I can say that the inner product of yn ym is equal to 0. So, from here I can say that ynx and ymx are orthogonal, because the same concept comes for the self-adjoint matrices. In the self-adjoint matrices, we know that self-adjoint means symmetric matrices, we know that the eigenvalues are real, and in that case we find out the eigenvectors. So, the eigenvectors are orthogonal to each other. So, same analogous things are going on in the case of eigenvalues and eigenfunctions. So, then the third property is that so, third property is that for the one eigenvalue there cannot be two eigenfunctions, and that is obvious that if we have a one eigenvalue and there is a corresponding two eigenfunctions, then the linear combination is also the solution of the given equation satisfying the boundary condition, and that is not possible because of the uniqueness. So, that is not possible that the one eigenvalue can have the two distinct eigenfunctions. Okay. So, now taking the next one is the third and fourth. So, fourth also, that in this case in the property fourth also we can have a infinite countable number of eigenvalues and then the corresponding eigenfunction, and then we have just defined that the eigenvalues are real. So, if they are real we can put it in the order, and then we can have the sequence of the ordering that we have defined, that the lambda 0 is less than lambda 1 is less than lambda 2, like that one. Okay. So, this one we can do, and then the property number 5. So, this is the another property just want to discuss here. So, in that case we have a function f x, any function, just I am taking a real function f x which is continually differentiable, and I am putting this value function is equal to summation a n, and this is y n x, and starting from 0 to infinity, like a 0 y 0 plus a 1 y 1 plus a 2 y 2, like this one. And what is this y 0 y 1 y 2? These are the eigenfunctions. So, in that case I can say that I am able to write a function f x in the series solution or in the summation of y n x. Now, and also we know that this y naught y 1 y 2 all are orthogonal functions. So, from here I am able to write like this one, then, and I am considering here that this series is convergent, in fact it is a pointwise convergent, and it is convergent to the function f x in the given interval that x belongs to alpha beta. So, this is I am considering. Then I know that, so I want to find the value of a n, like a 0. So, suppose I want to find the value of a 0. So, I will find out the value of a 0. What I will do is that I will multiply the equation, I just give it the name 2. So, I multiply this equation by a naught. So, what I will get a naught. So, this is the constant I want to find, f x is equal to a naught square y naught plus a naught. No, I just want to find the value of a naught. Then multiplying this equation 2 multiply equation 2 with respect to the function y naught x. and then integrate over the interval alpha beta. So, what I am doing now, I am just taking y naught x f x is equal to, it will becomes a naught y naught x square plus a1 y naught x y1 x plus a2 y naught x y2 x and so on, like this one, and then I am taking the integration with respect to x from alpha to beta. So, again alpha to beta dx, alpha to beta dx, alpha to beta dx and so on. So, I am taking the integration now. Just now we have found that this function y naught x and y1 x, they are orthogonal to each other with respect to the weight function Rx. So, now I can take multiply again with the Rx here. So, I can define this one as again multiplying the each with the Rx. So, I can write from here alpha x and then Rx y naught x f x dx, because sometimes the Rx can be 1 also. So, in that case the calculus will be, the calculation of this integral becomes very easy. But now what I am doing, I am multiplying like we have multiplied the y0 x, I am multiplying by Rx into y0 x. So, then it becomes so this is a naught alpha to beta Rx y0 square dx plus alpha to beta a1 I am just taking outside, it will be Rx y0 y1 dx and so on. Now, this part all will be 0 because they are orthogonal. So, from here I can find out that my a naught will be alpha to beta Rx y naught x f x dx divided by alpha to beta Rx y naught square dx. So, in this way I am able to find my value of a0. So, this is possible by only when we have the property that all the eigenfunctions corresponding to the different eigenvalues, they are orthogonal to each other. So, from here if I want to find any general value of an, then what I will do, I will again apply the same thing. I will pre-multiply the equation number 2 by Rx into yn x. Suppose I want to find the value of an, so I will multiply by Rx into yn x and then doing the integration with respect to x between the interval alpha to beta, and from there I am able to find the value of an. So, an will be in this case becomes alpha to beta Rx yn x f x dx, because I have multiplied by Rx into yn x divided by alpha to beta Rx yn square dx. So, then in that case my value of the an will be there, and then I am able to find all the coefficients. So, and this integral we can define very easily. From there I can find value of an, and then we are able to write the function in the terms of the series, and that series is made up of the functions yn, that is the eigenfunctions corresponding to the eigenvalues. If you just remember this one, this concept is almost similar, looks similar as the Fourier series. So, that we will do the Fourier series in the future, but this is just another series in which we are able to write a function in the terms of a eigenfunctions corresponding to the eigenvalues. So, in this case, so by this way we are able to find all the value of fn, and then I am able to write the function fx as summation n from 0 to infinity a n y n x. So, this is the concept we are doing here. Then just I will take the quick example that how we can solve a Sturm-Liouville problem. So, let us say take a example Sturm-Liouville problem like y double dash lambda y equal to 0, and then I take the initial boundary condition y dash 0, y dash 1 equal to 0. So, this is, you can say that this is a self-adjoint form, and in this case my operator is just d square over dx square. So, from here I can find out the solution. Now, from here if you see my px will be 1 and my rx in this case will be 1. So, this equation I can write in this form y double dash equal to minus lambda y, and if you see from here I can write this as a L. So, L is, so I can write this as a d square by dx square yx is equal to minus lambda yx. So, if you just write this one, I can write this a x is equal to some lambda x, this form, and this we know that this is the eigenvalue problem. So, this becomes the eigenvalue problem. So, from here I can find the solution, and if you solve this one I can find the solution of this equation. This is a linear equation, simple equation. So, from here I can find out the solution. So, this is a C1 cos under root lambda x plus C2 sin under root lambda x. So, this one I can find out, and then I put the boundary condition, then my y dash x in this case will be minus under root lambda C1 sin under root lambda x plus under root lambda C2 cos under root lambda x, and then I can put the boundary condition. So, from here I can put the boundary condition is y dash at 0. So, this will be minus under root lambda C1, and this is sin 0 plus under root lambda C2 cos 0, and that value is equal to 0. So, this part is always 0. So, from here I can say that because we are looking for the non-trivial solution, yx is always a trivial solution for this equation. So, we are looking for non-trivial solution, so, and my lambda is not equal to 0. So, I am from here I am taking that my C2 is 0. So, if my C2 is 0 I can find the value of C1. So, my yx is now C1 cos under root x, then I just from the another boundary condition that is at 1. So, from here my y dash x is minus root lambda C1, and then I will put my boundary condition y dash at 1. So, this will be under root sin, and this is given to me equal to 0. Now, I cannot have my C1 0, because if I take the C1 0 then it will be the just the trivial solution. So, from here lambda is also not 0, from here I can set the my under root lambda is equal to 0. So, from here I can say that my under root lambda can be written as, because we know this is 0, then from here I can write that my sin under root lambda is equal to sin n pi, and n is just value 0, 1, 2 and so on. So, from here I can write that my under root lambda is equal to n pi. That gives me that the lambda is n square pi square and n is 0, 1, 2. So, this is my eigenvalues, all the eigenvalues we are able to find. So, this is a infinite number of eigenvalues we are able to find, and then with the help of the eigenvalues I can find my eigenfunction. So, in that case my solution yx will be because C2 was 0. So, from here my solution is just cos under root lambda x, or I can call it cos n pi x, and n is 0, 1, 2, 3. So, this is the value function of n. So, I can call it as y in x. So, from here I can say that my y0 is just 1, my y1 x will be cos pi x, my y2 x will be cos 2 pi x, and so on. So, in this case my lambda will be, so lambda 0 will be corresponding 0, so it is 0, my lambda 1 will be pi square, my lambda 2 will be 4 pi square, my lambda 3 will be 9 pi square, and so on. So, from here I can say that my lambda 0 is less than lambda 1 and so on for the and this is the corresponding eigenfunction. So, this is the property third we have defined. So, this is true for this case, and then we can also show that this function, the eigenfunctions corresponding to the different eigenvalues are orthogonal. So, in this case my Rx is 1. So, I can check that from 0 to 1 if I take the integration and then I take any ynx and any ymx dx, then its value will be always 0 when n is not equal to n. So, this is my orthogonal properties, and that we can verify. So, this is the example of the Sturm-Liouville problem, and we are able to verify that when in the Sturm-Liouville problem our operator is a self-adjoint operator, it is a regular form, then the eigenvalues will be real, and for the distinct eigenvalue the corresponding eigenfunction will be orthogonal, and that orthogonal, and this will also form a sequence of the corresponding eigenvalues. So, thanks very much for this lecture. Thank you.